In this video, we're going to talk about double angle, half angle, and power reducing formulas. So once again, just make sure for this chapter that you're finding some way to study all of these formulas because there's a lot of them. So whether that's flashcards or making sure you write them at the top of your homework problems, those are great ways to help you study these formulas. So first we're going to talk about double angle formulas. So these are formulas for the following situations. So maybe we have sine of 2 theta, cosine of 2 theta, and I should really erase this, put it further down, and tangent of 2 theta. So notice double angle means that inside of sine, cosine, and tangent we have twice our angle theta. So for sine of 2 theta, we can say that this is equal to 2 times sine of theta times cosine of theta. Cosine of 2 theta, we actually have three different options. We can say it's cosine squared of theta minus sine squared of theta. But we could also say that it's 2 times cosine squared of theta minus 1. Or our third option is 1 minus 2 sine squared of theta. And then finally, tangent of 2 theta, we have 2 times tangent theta over 1 minus tangent squared theta. Okay, so like I've done in the previous sections, I think the most important ones of these three to memorize are probably the sine and then the cosine. So for identities, it's important to know all three versions of cosine just because any one of them could show up in a problem, and maybe you have to make some kind of substitution depending on what formula shows up. So it's good to know all three cosines, the sine formula. The tangent, though, once again, we could just take the sine and cosine and divide them. So it's not absolutely necessary that you know the tangent one, but that one is nice as well. Okay, so let's talk about why these are true. So I'm not going to prove all of these, but I'm just going to show you the first one. So the idea for all of them is to apply sum and difference formulas. So the one I'm going to prove for you is sine of 2 theta. So 2 theta, we can break up as a sum. We can say that this is just sine of theta plus theta. And from there, we can apply our sum formula. So sine of theta plus theta is going to be equal to sine of theta times cosine of theta plus cosine of theta times sine of theta. And notice that these two terms are identical, so we can actually add them together and put a 2 out front. So that's how we get our formula, 2 sine of theta, cosine of theta. So a good mental exercise would be to go through the cosine formulas and the tangent formulas and see if you can use similar sum and difference formulas to reach those formulas. So that would be a good exercise. Again, it's not homework, but it would be good. It might help you understand the formulas a little bit more, how they're all related. Okay, so let's get to some more concrete examples. So the first one we're going to do is we're going to find sine of 2x, cosine of 2x, and tangent of 2x, given that cosine of x is equal to negative 12 over 13, and x is in quadrant 3. So we've seen a lot of problems of this style in the past few sections. So the first thing you always want to do when you're given a problem where it says find, A, B, and C, and they give you one trig function and tell you which quadrant that trig function is in, or that angle is in, the first thing you want to do is draw the appropriate triangle. So we start with our 4 quadrants, and we know that our angle's in quadrant 3. So the triangle we're going to draw is going to be in the 3rd quadrant over here. So this is my angle x, and then I want to label my triangle based on which trig function I'm given. So cosine we know is adjacent over hypotenuse, so this means I need to assign negative 12 to the adjacent side and positive 13 to the hypotenuse. And if I were to do Pythagorean theorem to get the third side, I would find that it's negative 5. Okay, so now that I've solved this triangle, it's going to help me find sine of 2x, cosine of 2x, and tangent of 2x. So let's start with sine. So sine of 2x, the first thing we want to do is expand this out with our formula. So we have 2 sine of x, cosine of x, and so this is where my triangle comes in handy. So now I have my entire expression written with only x's. So we don't have any more 2x's, and this is good because our triangle is describing the angle x. So from the triangle, the sine of x is negative 5 over 13. And cosine of x, we already know, is negative 12 over 13. So now all I have to do is multiply all of these together, and we get 120 over 169. Okay, so if you haven't done too many fractions in the calculator, there's one button that's really handy. It looks kind of like this. So it's usually like an F with an arrow and a D. So what this button does is it actually takes your decimal and turns it into a fraction in simplest form. Okay, so if you haven't seen that before, that's a really handy button on your calculator, because remember that when we take a test, I'm going to want to see your answer in this fraction form, in simplest form. Okay, so you can practice that as well. Okay, so let's do cosine of 2x. So we have 3 choices for our formula for cosine of 2x, and it doesn't matter which one you pick. So I'm just going to pick the second one this time. So we have 2 cosine squared of x minus 1. So I'm going to do 2, and the cosine of x is negative 12 over 13. So we're going to have 2 times negative 12 over 13 squared minus 1. And if we put all of this into the calculator, we should end up with 119 over 169 as our cosine. Okay, and then finally we have tangent of 2x, which we could use our formula for, but I think it's a little easier since we've already found sine and cosine of 2x. We can just say that tangent of 2x is sine of 2x over cosine of 2x. So sine of 2x is 120 over 169. Cosine of 2x is 119 over 169. So if we divide these two fractions, we get 120 over 169 times 169 over 119. And so these 169s are going to go away, and our final answer is 120 over 119. Okay, so that is sine of 2x, cosine of 2x, and tangent of 2x. We're going to try another one of these, though, just to solidify the concept. So our next one, we're given that sine of theta is 8 over 17, and theta is in quadrant 2. So again, the first thing I'm going to do is draw the triangle. So theta is in quadrant 2, means that my triangle is going to be over here, and this is going to be my angle theta. And then sine of theta equal to 8 over 17 tells me that the opposite side is 8, and the hypotenuse is 17. So if I use Pythagorean theorem to get the missing side, I'll find that it's negative 15. And remember, just be careful with the negative signs. Depending on the quadrant you're in, the side you're finding might have to be negative or positive. Okay, so that's our triangle. And now let's start with sine. So we have sine of 2 theta is equal to 2 times sine of theta times cosine of theta. So from the triangle, sine of theta is 8 over 17. Cosine of theta is negative 15 over 17. So if I multiply these fractions together, I should end up with negative 240 over 289. So that's my sine. For cosine, I do the same sort of thing. I'm going to pick a cosine formula, and this time I'll pick a different one just so you can see how they're all used. So maybe let's say this time we do 1 minus 2 sine squared of theta. So if I plug in the value of sine of theta, I get 1 minus 2 times 8 over 17 squared. And if I put this into the calculator, I should get 161 over 289. So that's my value for cosine of 2 theta. And now for tangent, once again, we can just divide sine of 2 theta by cosine of 2 theta. So tangent of 2 theta is sine of 2 theta over cosine of 2 theta. And so we have negative 240 over 289 all over 161 over 289. And dividing these two fractions just gives me negative 240 over 161. So that's my tangent of 2 theta. Okay, so what we're going to do next with these double angle identities is practice proving some more identities. So for this first one, I do need to point out that I had a little typo. So this 2 right here should not be here. It should be inside of the sign. So instead of alpha, we're going to say sine of 2 alpha. Okay, so make sure you fix that. So I did have a little typo there. Okay, so first, remember to prove an identity, we pick the more complicated of the two sides. I would say that that's this left side because we've got that exponent there. So let's start by rewriting the left side. So we have sine of alpha minus cosine of alpha squared. And so remember when we square a parentheses, that means we actually have two identical copies that we want to FOIL together. So we have sine alpha minus cosine alpha times sine alpha minus cosine alpha. And if I FOIL these together, we get, I don't really need parentheses, so we get sine squared of alpha minus 2 sine alpha cosine alpha plus cosine squared alpha. Okay, so if I FOIL these out, combine like terms, I get the following trinomial. Now we need to decide, well, how can we combine some stuff together to where we get 1 minus sine of 2 alpha? Well, right away I notice I have a sine square and I have a cosine squared, and both of these are positive. So what I can do is I can say sine squared of alpha plus cosine squared of alpha is just 1. So those two terms turn into a 1, and we've still got minus 2 sine alpha cosine alpha. Okay, now that 2 times sine alpha cosine alpha, you might notice is that sine of 2 alpha formula we had in the box on the left. So that's formula number 1 right here. It's just we have alpha instead of theta. So I can substitute in for this term. I can say that's just sine of 2 alpha. And there we go. I've proved what I wanted to prove because I reached the right side using just a bunch of algebra. Okay, let's try one more. So this one, we have cotangent of x is equal to sine of 2x over 1 minus cosine of 2x. So this time, I think the right side looks a lot more complicated, so let's go ahead and start with that one. So I'm going to rewrite it. So we have sine of 2x over 1 minus cosine of 2x. So the first thing I'm going to do is just try to expand out as much stuff as possible. So on the top, I'm going to write my sine of 2x formula. So we have 2 sine x cosine x over 1 minus. Now cosine of 2x, remember we have 3 choices. Okay. So this part can get tricky because you might wonder, well, which of the 3 choices should I pick? Like, is one better than the other? And usually, yes, there is one choice that is better than the other 2. And so we're going to talk about which one that is and why. So first of all, we need to pick the formula that's going to get us what we want. And what we want is cotangent of x, okay? Which we know that cotangent is equal to cosine of x over sine of x. So because of that, I know that I want sine to appear in the denominator. Okay, so I'm going to make a little note of this off to the side. So we need to pick the formula for cosine of 2x that has a sine in it. And so that one is 1 minus 2 sine squared x. And we picked this because we want sine x in denominator. Okay, so again, that has to do with the fact that we want cotangent to appear, and we know that cotangent has a denominator of sine. So therefore, we're going to pick the cosine of 2x formula that has a sine in it. So in place of cosine of 2x, I'm going to write 1 minus 2 sine squared x. Okay, so just be careful with the parentheses there since we do have that negative sign. We're actually going to need to distribute that through the parentheses on this next step. Okay, so let's go ahead and distribute that negative sign through so it turns into 2 sine x cosine x over 1 minus 1 plus 2 sine squared x. All right, so 1 and 1, so 1 minus 1 goes away, and we're left with 2 sine of x cosine of x over 2 sine squared of x. So instead of writing sine squared, I'm going to split it up into its two factors because then I think you'll see the canceling a little easier. So now I have two factors of sine on the bottom and one factor of sine on the top. So that factor is going to cancel with one of these on the bottom. And the 2's will cancel as well because there's one on the top and one on the bottom. So all I'm left with is cosine of x over sine of x, and that's good because that's just cotangent of x, and that's what I wanted. All right, so this proof wasn't super long, but it was tricky because we had three choices for that cosine of 2x. So when you're going back and studying for test 2, this would be a good one to look at, not because I would necessarily put it on the test, but I think it's a good example of like how should you think through a proof? Like, where do you want to go? How do you need to get there? And like, what choices are going to make that possible? Okay, so that would be a good one to look at when you're reviewing. Okay, so the next type of formula we're going to talk about are what's called power reducing. So what this means is maybe we have something like sine squared of theta, and we want to get rid of that exponent. So the way that we do this is we take 1/2 times 1 minus cosine of 2 theta. And similarly, if we have cosine squared of theta, we can turn that into 1/2 1 plus cosine of 2 theta. So you might be noticing that these look really similar actually to the double angle formulas. So another good exercise might be to see if you can start with the double angle formulas and see if you can get to the power reducing formulas with some algebra, okay? But I won't verify them for you here. And then finally, third, we have tangent squared of theta is equal to 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. So once again, the most important ones to know are the sine formula and the cosine formula. I think this one makes it super obvious why tangent is just sine over cosine. Like, because as you can see, this formula is literally the sine formula on top, the cosine formula on the bottom. So it's really not a different formula from just knowing that tangent is sine divided by cosine. So let's look at an example of an identity. So we're going to prove the identity sine to the fourth of x is equal to 1 over 8 times 3 minus 4 cosine of 2x plus cosine of 4x. So this looks kind of complicated, but the reason I think it's important to show you is if your plan is to take calculus after this class, then you might see this happen a lot in certain problems where you're given something with an exponent and you need to break it down where you have no exponent. So this example is important for calculus, but even if your plan is not to take calculus, I still think it's an important algebraic exercise. So anyway, let's get started. So we have sine to the fourth of x, and while that may not seem like the more complicated side, I think when it comes to exponents, it's much easier to break them down into not exponents than to take not exponents and build the exponents up. So I'm actually going to start with sine to the fourth of x instead of the really long side over here. Okay. And so what I can say about sine to the fourth is it's really just sine squared of x squared. Okay, so what I'm going to do is I'm going to use that sine squared of theta formula, but I'm going to have to square it. So in place of sine squared of x, I'm going to write 1/2 times 1 minus cosine of 2x, and all of that's going to be squared. So when I square this, I'm going to square the 1/2, so I have 1/2 squared times 1 minus cosine of 2x squared. Okay, so the reason we can distribute the exponent is because the thing in the parentheses, the two things are multiplied together. Okay, we can't distribute an exponent across a sum, but across a product is fine. So 1/2 squared gives us 1/4, and then if I square the parentheses, I get 1 minus 2 cosine of 2x plus cosine squared of 2x. So now you might notice that I've still got an exponent here, but it's starting to look good, right? We've got a fraction out front, we've got a term that's a constant, we've got a term with a 2x, but we still need to take care of this cosine squared that's popped up again. So what I'm going to do is I'm going to apply my formula again. So I'm going to have 1/4 times 1 minus 2 cosine of 2x, and then in the place of cosine squared of 2x, I'm going to write 1/2 times 1 plus cosine of 2 times 2x. So it's important to note here that since our angle to start with was 2x, when I plug it into the formula again, it's going to double again. So just because it's doubled doesn't mean that we don't double it again. We need to make sure that we still multiply by another factor of 2, and that's going to give us that 4x that shows up in the answer that we want. So let's simplify this a little bit. So we have 1/4 times 1 minus 2 cosine 2x plus 1/2 plus 1/2 cosine of 4x. Okay, so I'm really close to my final answer. You might notice though that in the final answer we don't have a coefficient on cosine of 4x, but in our work down here we have a coefficient of 1/2. So my instinct would be to go ahead and factor out a 1/2 from all of the terms in the parentheses, and that's going to give us 1/8 on the outside and also get rid of that coefficient of 1/2. So if we factor out 1/2, we get 1/8 outside the parentheses, and then everything inside is going to double. So when you factor out by a fraction, it's like you're dividing by that fraction, which ends up multiplying. So in this case, we're going to end up with 2 minus 4 cosine 2x plus 1 plus cosine 4x. And that's what I want to happen, because now that looks almost exactly like that right side. I just need to add the two constants. So we have 1/8 times 2 plus 1 gives me 3 minus 4 cosine 2x plus cosine 4x. And so now I've reached the right side of that equation. Okay, so again, that one could have been a little confusing just because we had to apply the formulas so many times. So if that one gives you any trouble, make sure to ask me questions about it. Okay, we're going to try one more example. This could be any of the formulas we've done so far. So in this one, we want to simplify the expression but not evaluate. And we can't really evaluate because we've got x's in here. So we're going to try and get this into simplest form. So the first thing you might notice is that it looks very much like one of those double angle formulas. So we had like cosine squared of theta minus sine squared of theta, and that was equal to cosine of 2 theta. So that's kind of what we're keeping in mind here, except instead of theta, we have 9x. So all we're going to do is condense this down into cosine of 2 times whatever's playing the role of theta, which in this case is just 9x. So if I simplify the inside of that, we have cosine of 18x. And that's it. That is the simplified version of that expression. So this one was a little different because instead of starting with a double angle and using the formula to expand it, we started with the expanded version and condensed it down into a double angle. And sometimes that's useful too. Like, again, if your plan is to take calculus after this, you'll find that a lot of problems will want you to do this because maybe the problem is easier to solve when you have it in the double angle form versus an exponent. Okay, so it is like you're going to use these formulas later on down the road again. It's not like you're just studying them for nothing. All right, the last type of formula we're going to talk about in 7.3 are what we call half angle formulas. So these look like the following. So for example, we might have sine of theta over 2, and that would be equal to plus or minus the square root of 1 minus cosine theta over 2. Or maybe we have cosine of theta over 2, and that's equal to plus or minus 1 plus cosine theta over 2. Or finally, we could have tangent of theta over 2, and that's just plus or minus 1 minus cosine of theta over 1 plus cosine of theta. So once again, the most important ones to know would be the sine one and the cosine one, because I think from there you can get the tangent one pretty easily. All right, you're just dividing them by each other basically. And so one thing you might be wondering is, well, how do we take care of those plus or minus signs? So technically that means you get two different answers, which happens a lot when you're dealing with square roots. But when we're talking about sines and cosines and tangents, you can't have both signs at the same time. Like it's only one, it's either positive or it's negative. So the way that we choose between those, so we're going to pick plus or minus depending on quadrant of theta over 2. So this is important because a lot of times people get theta and theta over 2 confused. And most of the time they will be in different quadrants. So you're not paying attention to the theta that you have to find to help you do the formula. You're paying attention to theta over 2. Okay? And that'll make a little more sense when we do an example. But this also requires you to remember where each trig function was positive or negative, and we did that way back. Like that was one of the first things we did. So if you don't remember that, make sure to go back and review that. Okay, so we're going to jump into some examples. So let's find the exact value of the following expressions. So the first one we have is in degrees. We have sine of 22.5 degrees. So our goal here is to find an angle so that 22.5 is that angle divided by 2. And the way we can do that is just set up this little equation to help us, and we can just multiply by 2. And that gives us that theta is going to be 45. Okay? So the way I'm going to write this is sine of 22.5 is really sine of 45 degrees over 2. And so we're going to use our sine formula, which is plus or minus the square root of 1 minus cosine of 45 over 2. Okay, so at this point, this is where we need to decide, is our answer going to be positive or negative? So 22.5 is in quadrant 1 because it's between 0 and 90. So our answer for sine is going to be positive. Okay, so from here on out, I'm not going to write a sign or a positive or negative sign next to the square root because I've decided that it's positive. Okay, so we have the square root of 1 minus, now the cosine of 45 degrees is root 2 over 2, and all of that's going to be over 2. So now I just need to simplify this expression. So, got my big square root, And then 1 we can rewrite as 2 over 2 minus square root of 2 over 2 all over 2. So these can get kind of tricky because there's a lot of fractions within fractions, a lot of square roots running around, so just make sure that you keep all of that straight. Okay, so we can subtract the two fractions. So we have 2 minus root 2 all over 2, and that whole fraction's over 2. So what this does is it actually, so if you come up here, this actually gives me the square root of 2 minus root 2 over 4. So we have 2, and then we're dividing by another 2, so that's going to give me a 4. But now I can take the square root of the top, which doesn't really do anything. I'm just going to write the top under a square root, but I can square root 4 and just get 2. So my final answer is going to be this ugly nested square root mess of the square root of 2 minus the square root of 2 all over 2. But those square roots are nested. Okay. So these can look really nasty, but this is your exact value of the expression. So let's try another one that's going to get even nastier. Okay, so this time we have sine of pi over 16. So first of all, pi over 16 is equal to pi over 8 divided by 2. But that's a problem because pi over 8 is still not a nice angle that I know values for. So we're going to have to take pi over 8 and say, okay, well pi over 8 is pi over 4 over 2. And so we'll see where this gets us in our formula. So first we're going to say that sine of pi over 16 is pi over 8 over 2. And so we're going to go ahead and write the formula for that and then see where the second pair of angles comes in. So our sine formula is plus or minus the square root of 1 minus cosine pi over 8 all over 2. So now I have cosine of pi over 8 inside of my formula, but I don't know what cosine of pi over 8 is, because pi over 8 is not an angle on our unit circle. So what I'm going to do is come off to the side and use a formula again to find cosine of pi over 8. So we know cosine of pi over 8 is cosine of pi over 4 divided by 2, which is the square root of 1 plus cosine pi over 4 all over 2. So this thing on the right here is going to be similar to the example we just did. So we're going to have the square root of 1 plus root 2 over 2 all over 2, which gives me the square root of 2 plus root 2 over 2 over 2, which again gives me 2 plus root 2 over 4, which I can square root that 4 and get square root of 2 plus root 2 all over 2. So I'm going to take this here. Come on, highlighter. Come on. Okay, well, I'm going to take this thing on the right, and I'm going to plug it in for cosine of pi over 8 over here. There we go. Okay. So I'm going to take that fraction on the right and plug it in for that thing that I highlighted under the square root. So this is going to get a little complicated, but it's going to be okay. So I'm going to have 1 minus square root of 2 plus square root of 2 all over 2 all over 2. And I've decided to take the positive version of the square root because pi over 16 is again in quadrant 1. Okay? So now I need to simplify the thing under the square root. So if I get a common denominator of 2, I have 2 minus root 2 plus root 2 all over 2 all over 2. And the 2 divided by the 2 is going to give me a 4. So this turns into the square root of 2 minus root 2 plus root 2 all over 4, which if I then square root the 4, on the top I have square root of 2 minus square root of 2 plus square root of 2, all nested together, over 2. So this is the exact value of sine of pi over 16. So once again, if all of the square root arithmetic gets confusing, please let me know. Please ask questions. Okay. All right, so let's go back and do another example. So this one we're going back to the idea of a double angle formula. So it looks a little complicated, but what I want you to think about when we're doing this one is cosine of 2 theta is equal to 1 minus 2 sine squared of theta. And it really doesn't matter which of the cosine 2 thetas you pick, but the important thing to notice is just that this actually is a cosine of 2 theta situation. So that inverse tangent thing on the inside that looks really gross is really just playing the role of theta. So the first thing we can do is actually expand this out using a double angle formula. And I've just decided to pick this one. So we have 1 minus 2 times sine squared of tangent inverse of 12 over 5. Okay, so maybe just as a reminder, when I write this exponent next to the sine, what I'm actually saying is that this entire expression is squared. So my goal now is to figure out what is this sine of tangent inverse of 12 over 5. So to do that, I'm going to draw a triangle, and here the quadrant, it's not quadrant specific because, well, it kind of is, but we have 2 quadrants to pick from, but 12 over 5 is all positive, so I'm just going to pretend like it's a quadrant 1 angle. So this is my angle theta, and tangent of 12 over 5 tells me that the opposite side is 12 and the adjacent side is 5. So using Pythagorean theorem, my hypotenuse is 13. So now I can say that the sine from this triangle, the sine of theta, is going to be 12 over 13. So I can plug that into this formula at the top. So this just turns into 1 minus 2 times 12 over 13 squared, which if I multiply this all out, just gives me negative 119 over 169. All right, so just be careful putting that into a calculator, and you should get the same fraction. Okay, so let's remind ourselves what we did here. So first, we recognized that this problem was actually just cosine of 2 theta in disguise, with an ugly something playing the role of theta. So we picked a formula for cosine of 2 theta, and we expanded it out, and then we used a triangle to figure out what that inverse tangent was actually telling us. Okay, and then we just simplified using arithmetic. So let's do another one kind of like this, but we're not going to have inverse functions in this one, but it's going to be similar to when we found like sine of 2x, cosine of 2x, and tangent of 2x. So we're going to find sine of theta over 2, given that tangent theta is negative 5 over 12 and our angle's in quadrant 4. So the first thing that we should note, since theta is in quadrant 4, theta over 2 is in quadrant 2. Okay? And also, that's going to tell us that sine is positive and cosine is negative. So in quadrant 2, our x-coordinate's negative, our y-coordinate's positive, so that's how we get these signs for sine and cosine. Okay? So let's go ahead and get our triangle. So quadrant 4 is going to look like this. Our triangle is going to be in that bottom right corner. And this angle right here is going to be theta. And since tangent's negative 5 over 12, we're going to have negative 5 as the opposite side and positive 12 as the adjacent side. And I picked the negative sign to go on the vertical side because we're in quadrant 4, so we know that the y-coordinate is negative, the x-coordinate is positive. Okay, so let's start with our sine of theta over 2. Oh, and I didn't even solve the triangle. Look at me. Okay, so let's find the hypotenuse with Pythagorean theorem. That's just going to be 13. So now we can go to our formula. So we have sine of theta over 2 is equal to the square root of 1 minus cosine of theta all over 2. So on the square root, I've picked the positive sign because in quadrant 2, we said sine is going to be positive. Okay, so that's why my square root does not have any sign on it. And now what I'm going to do is plug in cosine of theta. So we don't know theta itself, but we can get the cosine from the triangle. So the cosine from this triangle is going to be 12 over 13. So we have adjacent over hypotenuse. And 1 minus 12 over 13 all over 2 is under the square root. So now we can say 1 is equal to 13 over 13 minus 12 over 13. Maybe consistent with the fraction bars there. So we have 13 over 13 minus 12 over 13 all over 2. So subtracting those two fractions on the top gives me 1 over 13 over 2, which gives me the square root of 1 over 26, which I can split up into the square root of 1 over the square root of 26. And so I just get 1 over the square root of 26. All right, so that's the sine of theta over 2. So you could do similar things for cosine of theta over 2 as well as tangent of theta over 2. Same process, just make sure you're using the correct formula. And I should also remind you that if you end up with a square root in the denominator of an answer, I'm totally okay with that. You don't have to rationalize denominators because if your plan is to take calculus after this, they're going to tell you that they want square roots in the denominator. So I'm not worried about whether you can fix that. All right, the last problem that we're going to do in 7.3 is we're just going to prove an identity using half angle formulas. So we have the identity tangent of x over 2 plus cosine of x times tangent of x over 2 is equal to sine of x. So I think we can all agree the left side is definitely more complicated, so that's the side I'm going to start with. So I'm going to rewrite it. So I have tangent of x over 2 plus cosine of x times tangent of x over 2. And maybe the first thing I do is just factor out tangent of x over 2. And so what I'm left with is 1 plus cosine of x. So in that first term, since we factored out tangent of x over 2, we weren't left with anything per se, so we make sure that we keep that term by using a 1. Okay, so now tangent of x over 2, we have a formula for that, and that's just the square root of 1 minus cosine of x over 1 plus cosine of x, and we still have 1 plus cosine of x over here. Okay, so what I can do with this square root, the good thing is that the stuff under the square root looks similar to the stuff that's not under the square root, so we're probably going to be able to cancel some stuff, but I'm just going to rewrite it in a way that makes that more obvious. So first of all, we can split up the two parts of the square root. We can put a square root on the top of the fraction, and we can put a square root on the bottom of the fraction, like this. And then I can rewrite 1 plus cosine of x as the square root of 1 plus cosine x squared. Okay, so remember, anytime you have something without a square root, it's really just 2 copies of the square root. So it's the square root raised to the second power, which is good because now that I've written it in this form, we have 1 copy of the square root in the denominator, 2 copies of the square root in the numerator, so one of those copies is going to cancel out. And so what we're left with is the square root of 1 minus cosine x times the square root of 1 plus cosine x. And so now, when I multiply 2 square roots together, I can multiply the 2 things underneath. So I get one very big square root, with 1 minus cosine x times 1 plus cosine x underneath. And if I FOIL out these parentheses, I get the square root of 1 minus cosine squared x, which you might recognize is just the Pythagorean identity, cosine squared x plus sine squared x is equal to 1 in disguise. So all they've done is moved over cosine squared x, and so sine squared x is equal to 1 minus cosine squared x. So under the square root, we can go ahead and sub that in. So we have the square root of sine squared of x, which if we take the square root of a square, we just end up with one copy of the thing. So here we had 2 copies of sine x. We're square rooting it, so we're just going to be left with plain old sine x, which is exactly what we wanted. That was the right side of our identity. Okay, so there were a lot of formulas in this section, so if any part of this is confusing, please let me know. And this concludes our lesson for 7.3.